iC-Haus. Integrated Circuits.
Good morning, good day, good afternoon. Welcome to iC-Haus webinar series 2022. We will start today with the new magnetic sensor, which is going to using the TMR technology, and I'm joined today by Mr. Joachim Quastorf and Mr. Patrick Stahl. And before we start today's webinar, I just want to take you through the webinar tool. The webinar tool has a control panel, so you can click here on the red button to open and close the panel. In this panel, you have a question and answer session. In this box, you can place your questions and you can send them to us. The webinar team here will then work on it and send it over to me at the end so we can start the Q&A session. And I encourage you to ask as many questions as you have. We will do our best to answer to them timely during today's session. Should we run over, the session will be recorded and your questions will be answered. So we look forward to many questions from you and an interactive session. You have two screens. The top screen actually shows the speaker and the bottom the presentation. And in the middle, you have a cursor and you can move up and down so you can size up the screen you like to see in the larger mode. So just be careful when you move up and down. Don't go all the way up because then you might lose the speaker screen. So with that said, I would like to pass on the word to Mr. Joachim Quastorf, who's going to take us through today's presentation. So welcome, Joachim.
Thanks, Henrik. Hello, welcome. My name is Joachim Quastorf and I'm responsible for sales and applications engineering for optical and magnetic encoder systems. Since interpolation ICs are my specialty, I have to deal with many different types of sensors, quite often with magnetic XMR sensors. And that's what we are going to talk about today. I will be assisted by Patrick Stahl, who will do the hands-on demonstration later. Our focus of today will be solely on end-of-shaft angle sensors, and I will try to explain what we, as application engineers, need to know about Hall and also XMR technologies. And quite interesting part will be on performance, resolution, accuracy. Before I will take some more words on the TW39, introducing all its features. In the second part, Patrick will take over a live demonstration, and finally we do have time for your questions at the end. Now, when looking at our angle sensor portfolio, from left to right, we start on the left with 6-bit resolution, and currently the iC-MHM offering 14-bit resolution as a maximum. When asking for higher resolutions, usually those systems prefer off-axis applications, off-axis systems like shown here. Most of them are running incremental, could be powered by MR sensors or also using Hall sensors as shown on the right-hand side. Well, the TW39 is a new item now based on TMR, and we can higher the resolution now to 24 bits. We have to take a deeper look. Well, you may see all those Hall sensors have their specific focus, either on incremental output, on analog output if it's sine, cosine, or radiometric, on motor control, and then on single-turn absolute and also multi-turn gear encoders or battery-powered multi-turn encoders. And additionally, for ultra-low power applications like human-machine interfacing, we got the TW11. Now, the new TW39 extends the resolution to an extreme way, and it aims at high-resolution absolute and incremental applications. And whenever you are heading for absolute encoders, having the speedy BIS interface embedded on the chip is an advantage you won't like to miss. Let us take a deeper look. Well, the good news is the TMR is not just higher in the resolution, it's also rising the flag for accuracy. Where we usually can expect 0.3 degrees from Hall sensors, we now have 0.1 degree at hand from the TMR. Another point worth to mention is latency. Where the Hall sensors need to employ an advanced circuitry to cancel the offset, and also filtering adds a lot of latency. Here the TMR is a lot faster. Modern processors are compensating their latency, and so the output lag is reduced down to 1.5 microseconds. That's already on the level as you get it from optical encoders. Sounds like everything is ideal, but it's not quite the case. We have to consider some measurements for conditioning. Same as the Hall sensors needed, for instance, an automatic gain control to stabilize the signal. Also, the TMR sensor is not error-free. It gets errors from the sensor itself and from the application, so we need to deal with that. And the news for now is we don't need to worry. We can do that fully automated. Regarding other features, I think you won't miss what you are used to have. For instance, an arbitrary ABZ output, any count from 1 up to 65,000. Same as for UVW commutation signals, those are offered. Some more features, you may like to have a multi-turn interface. Also, this is included, or an SPI for embedded applications. Finally, the very good news is the EPROM is on the chip, so that the form factor is just 5 by 5 millimeters, allowing you smaller encoder designs. Now we have to check out some generic characteristics. What makes the difference between the Hall sensors, typically the quad Hall sensor array as shown here on the left side, and the TMR sensor as shown here on the right side? Well, first of all, the Hall sensor is detecting the vertical field gradients, and this fully differentially to derive an angle from this. Not so the TMR sensor. It's the chip it's quite tiny, more or less in the center, but it reads the angle in the vertical, in the planar XY chip field. Now, regarding sensitivities, we get only a few microvolts from the Hall sensor, given a typical field strength we get from a magnet. The TMR sensor offers us more than 50 times the level at the same field strength. Some of you may be familiar with AMR sensors. I need to say that the efficiency of the TMR is way above the AMR. So the AMR gives us just 1/12 the level as the TMR, and we need to amplify it. What means you add cost for proper amplification, and also maybe noise, as any amplifier is a critical issue regarding the signal-to-noise ratio to maintain it. Well, the amplitude temperature coefficient, Hall versus TMR, we have just 1/4 as the Hall sensors provide. So this is very low. Again, the comparison to the AMR, we are at least twice as good as the traditional AMR sensor. Signal offsets is another concern. The Hall sensor must employ on-chip circuits to cancel the offset generated by the sensor cells. Not quite so. The TMR, it is relative to the amplitude, it's quite small. But of course, when heading for high resolution and high accuracy applications, we need to consider cancellation corrections. Well, as said, the detection of the differential field gradients, that's what the Hall sensor does, is totally different. So it needs to be narrower, closer to the magnet to get a good reading. Not so the TMR sensor. We look at the planar field angle, what means that also the sensor can be far away from the magnet. So this adds on a higher air gap tolerance for your application. You can allow motor axis which has some play. In comparison to that, the Hall sensor scores with an excellent stray field immunity due to this differential field of cells. And it allows us a cost-effective monolithic integration. Now, what are the physical weaknesses? Of course, when heading for high accuracy angle sensing, we need to install a magnet supporting this. So selecting the magnet in size and also placement diameter, placement distance, that is a thing what you need to optimize. And it's hard to say to what amount imperfections, like shown here, magnetization, which is not directly symmetrically in the center, how this imperfection can be tolerated or not. Well, it does make more sense to compare finally the the angle measurement result to a reference to see what is good. Finally, if assuming the magnet is perfect and the XYZ positioning of the sensor is almost ideal, well, we will have some surviving harmonic signal distortion, which ultimately limits our sensing performance. Some of it is sensor-specific to the TMR as well, or to the Hall, of course. But the majority is simply quite easily dominated by the magnetic field quality. Using a poor magnet will limit your results. How about hysteresis? Well, regarding angle hysteresis, the Hall cell itself does not know that. For the TMR, we specify 0.04 degrees, meaning 140 arc seconds. And the AMR does about 0.2 degrees. Well, considering that the Hall signal must be amplified and also the AMR signal must be amplified, those circuits will add some noise. And finally, we need to see that the Hall sensor requires an electronic hysteresis to quieten the AB output. So overall, angle hysteresis scores best for the TMR. It is the lowest. Well, we have other things. Stray field is a concern. The sensitivity is generally high for TMR and AMR, and that's what I need to explain you. Now, assuming we get a magnet as interference, the sensor is reading the superimposed field angle. And our measurement results, the angle gets deviated from the origin. Now, how can we avoid this? There are just two measures against it, either keeping a distance, or maybe that's not possible in your application. When you are close to a disturbance, to a motor brake or whatever, keeping distance is not always possible. The other alternative would be to add a shield. This can easily be done by adding a ferromagnetic guard ring, avoiding the intrusion of the external stray field. Now, regarding performance measurements, I decided to take one system each for all the technologies. So this was for the Hall sensor. It was the iC-MH3 Hall sensor, providing us sine cosine over 360 degrees with an amplitude of about 500 millivolts. For the AMR, I used the PVL3M evaluation board, what we also offer for evaluations. It is equipped with Sensitech 746 advanced AMR angle sensor. So this is an angle sensor which is relaxing the reading distance, especially as it runs already beyond 5 kiloampere per meter in magnetic saturation, and that is required for those strong field sensors. This board is also equipped with the PVL as a low-power battery multi-turn, But in our case, we are using its single-turn sensing to decide if we read the first or second cycle of the AMR signal. And of course, I got the new 39er on a different board to compare it. Well, I missed to mention the sensors providing sine-cosine signals have been evaluated. They have been powered at 3 volt and evaluated by the TW39 simply as it offers us a push-button calibration to get rid of all those sensor errors. Well, when looking at the operating distance, we can easily see the Hall system needs to be closest to the magnet to get a proper sine-cosine output with low harmonic distortion. The broadest air gap is allowed by the AMR sensor. That is due to the advanced design here. So this can be far away from the magnet and we can still get a good angle reading. The TMR is somewhere in the middle, but we have still more air gap at hand as from a typical Hall system. Regarding the alignment tolerances, well, the Hall sensor needs to be quite close, quite accurately positioned. For the XMR, it's a little bit better. And especially, I would like to say, for the radial misplacement, the TMR gives us an even more tolerance. I need to mention position lag. Well, modern interpolation devices, such as the TW39, are able to compensate their digital latency by countermeasures. So the output lag can be reduced to just 1.5 microseconds. But not so for this is a benefit when using the XMR sensors, but not so when you connect the Hall sensor. Whenever you connect a Hall sensor or a front end, adding some latency, you get it on top, as this cannot be compensated afterwards when you connect an interpolator. Well, it could be one device, but that's not currently there. Okay, regarding all my benchmarking results, I got already a summary here. We can expect that we get hi-fi signals, meaning that our harmonic distortion is well below -50 dB. I'd like to mention this as a precondition. When heading for high accuracy measurements, it's a precondition to have low harmonic distortions, otherwise we cannot reach our goal. Regarding the accuracy results, we can see that the arm error and also the TMR perform twice as good as a traditional Hall. In my comparison setup, I need to mention this. How about noise in those systems? Well, we decided to determine a noise-free resolution simply as this is also a value which says up front, down to which level you can reduce your hysteresis. Well, the hysteresis is what is needed to keep AB quiet. Here we can easily see that the TMR scores best. It is twice as good as the other systems. So we have the high INL accuracy, we have the minimum noise, and finally the best or the lowest electronic hysteresis required for quiet position reading. Well, I decided to set up a measurement taking many samples of those systems, and this evaluation leads to a histogram. This was captured with a bin size of 20 arc seconds. It's the noise distribution of an angle at standstill. I need to mention you need to switch hysteresis to 0, otherwise you don't have any distribution. Well, we can easily see that AMR and Hall performs almost equally the same. And the yellow, representing TMR, is a little better visible. Its distribution is narrower. The green bar is just for comparison. It was taken from the optical reference. Now, when zooming in, we can see it a little bit better here. TMR is definitely shows a smaller distribution. And as said, we decided to determine the noise-free resolution, as this is a good value to learn something about the sensor performance. Now, this is shown here. We could easily determine also the 1 sigma standard deviation, as this distribution here is quite a good Gaussian distribution. We decided to use this 3.3 sigma for, it gives you us smaller numbers, but we decided to use this, as this tells a word about the hysteresis. Now, comparing the three systems I'm introducing here, we see that the TMR is better than AMR and Hall. But keep in mind, it's all about filtering. It can be possible to add more filter on the Hall or on the AMR signals, and this gap can be smaller. But keep in mind, whatever you do, it's at the expense of latency. Well, when looking at systems, the first question is often on resolution. When asking for higher resolutions, this question is often answered by off-axis systems, like shown here. Those systems can be equipped with the ICMU Hall sensors, for instance, or they can use a traditional MR sensor like the SM2 we offer in combination with an interpolator generating RC quadrature output. Well, these pole wheels offer many pole pairs, what we don't have on the on-axis or the end-of-shaft application. However, using the TMR sensor, we can easily reach a much higher resolution. Resolution is not everything. How about accuracy? Well, again, let's do the comparison. Aiming at 0.1 degree may be answered by the off-axis system, as I just said. But using the TMR, we also can gain 2 more bits, so that we now reach almost the level, the accuracy level of also the off-axis systems. So that is an advantage, giving you more application flexibility. Now, not the whole world is magnetic. So you may ask about, can we replace optical encoders? That's a good question. We need to take a deeper look. And I would say yes and also no. Yes, likely for the resolution. You can easily generate, if you have 24-bit resolution at time, you can easily generate 2,500 cycles, A-B signals, with also a good jitter quality. But this is the differential nonlinearity. Well, when it comes to the integral nonlinearity, I would say no. The optical encoders easily reach values better than 100 arcseconds. Well, the root cause must be clear. The optical code disk is at least 10 times more accurate than any magnetic target you can have. So bridging such a gap is not an easy task if coming from a low resolution magnetic scale or magnet. Now, I'm now introducing the TW39, our new 24-bit magnetic on-axis angle sensor. It tracks very high speeds, up to 360,000 RPM. And as explained, we also allow a much higher variation in the air gap. Looking at the angle processor, It features digital error corrections as needed to get rid of the primary signal errors. Also, this kind of sensor provides us. And there is a INL correction, which is a static correction eliminating the long wave position error. Digital filtering helps us a lot to smooth the position reading and also to generate AB signals, which are excellent in AB jitter quality. The engine owns a revolution counter, which is just a counter capturing the revolutions, but you could also preset it. I will explain it. As the chip runs at 50 megahertz, we get an update rate of 20 nanoseconds for our position grid. Due to latency compensation, the output lags not more than 1.5 microseconds. Selecting hysteresis is up to you. You can have it between 0 and some degrees. The Speedy BIS interface included is first of all an open source interface allowing high clock frequencies up to 10 megahertz and is permanently bidirectional. So you have full register access over BIS. The chip owns the BIS profiles 3 and 3S. 3S for safety, so that you also can enable a 16-bit CRC and a sign of life counter for the data output. So this output complies to the BIS safety protocol we defined. The data you can get is the 24-bit multi-turn data. That's optional, along with the single-turn data up to 24 bits. ABZ UVW outputs, they allow you a flex count resolution from 1 up to 65 something pulses. The edge distance is adjustable. That's an important feature, so that you don't override your external counter. The index is adjustable. You can set the 0 position. You can define its length or the gating to AB. When switching to UVW commutation signals, you can configure between 1 up to 32 cycles, and again, the commutation angle can be preset. All those angles are independently preset, ABZ and UVW and also BIS. Now, if heading for absolute systems, it can be an advantage to have the absolute data interface included. So this allows you to connect up any revolution counter you have. This engine is quite flexible to process serial BIS or SSI data. Now, for setting up operation, it's quite handy to have this push button calibration. There's also a reset button, also an alarm output and input. Usually at the output you connect an LED as an alarm indication, but it can also read in a system alarm to get an output of this BIS error bit. Preset pin is an important thing. You can zeroize your BIS position data, your angle. The engine owns digital monitoring, actually digital Lissajous monitoring, and some more features allowing you some kind of condition monitoring to check if your motor axis is still running as expected. So you can alarm on errors which cannot be compensated anymore upfront before the whole system will fail. We got also a temperature sensor included, allowing you to monitor the device temperature and to set up an alarm if the maximum operating range is reached. Alarm output input is bidirectional, that's what I mentioned already. There is an SPI interface additionally available besides BIS. So this allows you an extension connecting external microcontroller if you need to implement more memory on electronic data sheet for your device or some user commands. I need to mention that from BIS, you can directly inquire or you can tunnel down via SPI to your MCU. So this gives you the highest flexibility for the whole system. Well, it takes some power. The chip runs at 3.3 volt, but we are just about 100 milliwatt and full temperature range is covered. Now, that's a picture of our evaluation board, what we will see shortly in action. This board features a BIS connector as input and a BIS output connector and some terminals for the ABZ, respectively the UBW signals. And there's also an SPI terminal, but that is not required to use it when you connect over BIS. The sensor is actually not visible, it's here placed on the back. You may have seen it on the slides. It's a tiny device, 5 by 5 millimeters. Well, now I'm handing over to Patrick for the live demonstration.
Thank you very much, Joachim. Yes, hello and welcome also from my side. My name is Patrick Stahl. I'm Sales Application Engineer at iC-Haus. Today I want to give you a live demonstration of the new iC-TW39 chip. So let's dig in here and go to the demo setup and I show you what we have here. So first of all, as you can see, we have a motor here that hosts an optical reference encoder with BIS interface. Then we have here our XYZ manipulator that allows me to position the TW39 1M board relative to the magnet that is mounted on the motor here. The magnet is a 12 millimeter diameter magnet. It's a high precision magnet that is especially suitable to reach the highest accuracy with iC-TW39. This magnet is also available as a 9 millimeter version. Of course, you can use also other diametrical magnets with it, but you might not reach the optimal performance with it. Then we have here connected to our ABZ outputs of the boards a scope that you can see here in the background. We have the BIS interface here that interfaces to our reference encoder that is mounted in the motor, forming a BIS chain. And then this BIS chain hooks up to the BIS master, which then interfaces to our demonstration computer here that's running the demo software also. And everything is externally powered, of course. All right, so I will switch over now to the demonstration software. Hopefully you should be able to see my screen now. You can see that we have a position reading here from the sensor. At the moment is set to 24-bit. So you can see this changes when I turn here. We will set the ABZ output to 2500 CPR. That's cycles per revolution. That equals 10,000 increments per revolution. And then here we have an absolute accuracy measurement or nonlinearity graph. You see the reference angle on the x-axis, and on the y-axis you see the absolute angle error against the reference encoder in between -1 and +1 degree. As you can see at the moment you see nothing, so let's switch on the motor so that the system starts to run and we actually see an error curve here. So as you can see, this currently this looks pretty horrible. This is because the sensor is not yet aligned to the magnet. Also, if you have a quick look here at the scope, you can see that here on the yellow A channel output of the encoder we have quite a large edge jitter. So what I will do now, I will move this board over the magnet and try to align it a bit in this direction here, using my trustworthy blue arrow here to indicate. Let's give this a try and have a look at the nonlinearity graph here. While I'm doing this, I'm pushing it forward now. And you can see it improves a lot. All right. So the accuracy is already pretty good now, but of course we can further improve this accuracy using the push-button calibration feature of iC-TW39, like Joachim explained earlier on. So I will push the button here on this evaluation kit and then basically let the algorithm of TW39 work. And here you see the result. The error curve is very nice. I think this accuracy is well below 0.1, plus minus 0.1 degree here. Also, if you look at the scope screen now, you can see that also the jitter improved tremendously. We have one full period of the A signal here on the scope of about 10 boxes. And so one box is a 10% jitter. And as you're probably able to roughly see here, we're maybe at a plus minus 1 to 2% jitter here, which I think is a very good result for an on-axis magnetic encoder. Also, what I can do now, I can vary the air gap a bit. So this manipulator allows me to vary the air gap by 500 micrometer per turn. I will do now a couple of turns. So maybe 1.5 millimeter change. And you still see there's not much change to the absolute accuracy. There's also not much change here to the jitter of the system. As Joachim explained earlier, this is because the TMR sensor measures the field in the XY plane, so it's very insensitive to these kind of changes of the air gap. So let me adjust this back again to the starting position where we did the calibration at. Okay. So now, of course, you can say, well, this all works very nice at room temperature, but what about heating up the system? What happens then? I'm pretty sure the TMR sensor introduces some error, and then the whole error curve and everything, and the jitter doesn't look that nice anymore. All right, let's give it a try. Joachim, please bring the air gun here. Safety first. Put on my safety glasses. And here we have the air gun. Switch this on. This air gun is set to 100 degrees Celsius, so it's not too hot. Nevertheless, I would like to point out to you, our evaluation kits are not made for high temperature testing, so please don't do this in your lab. So I'll heat up the system now. And as you can see on the screen here, there's also a temperature display on the bottom of the nonlinearity graph. This is a built-in temperature sensor of the TW39, which is also a very nice feature. And as you can see, the system is heating up now. We are already at about 60 degrees now. I'll try to push it a bit further here. Try to really get some heat into the system here. And as you can see on the nonlinearity graph here, not really much is changing. And also, if you look at the jitter performance on the scope here, you also see the jitter doesn't change much. Give this back to Joachim again. All right. So this is because basically when the system heats up, the TMR will introduce some errors, but as Joachim explained, the TW39 has a dynamic error correction, so it detects these errors and removes from the signal to always keep the system at the optimal performance. And also, as you saw when heating up the system, there's not much more jitter introduced, and this is also because TMR sensor has a very low temperature coefficient. That means that the signal amplitude only falls slightly when the temperature is increasing. This concludes my live demonstration, and with that, I hand over back to Joachim. Thank you.
So I'm back. Well, thank you, Patrick. You have been a little bit careful with the temperature. Why not go at 120? Well, at worst case, you would burn the connectors, but who cares? Okay, thank you anyway. Well, I'm back with a summary of the system you just have seen. So it provides you the best-in-class resolution up to 24 bits per 360 degrees. And the outstanding accuracy, well, the zoom-in was not demonstrated here, but believe me, it's possible using a precision magnet to go well below 0.1 degrees. At least the ultra-low hysteresis is something what you may not be used to, as all other magnetic systems are higher than that. The engine is speedy. We allow very high frequency input up to 6 kilohertz, meaning 360,000 RPM of your drive are not any problem. The high axial play tolerance was demonstrated. This is just a raw number for the magnet we used here. different magnets can lead to different results. The output lag is extremely low, compensated by latency down to 1.5 microseconds. Self-calibration for ease of commissioning was demonstrated, and the chip runs at 3.3 volt, 100 milliwatt full temperature range. As already mentioned, the expandable option here, connecting an MCU over SPI, will give you some more flexibility. And in the setup we demonstrated, we accompany the BIS output along with the ABZ quadrature output. Well, so we are at the section end, and so this gives us time for your questions.
Thank you, Joachim. Very good. We have a lot of questions, and I think we have about 4 minutes left of this recording. So just be aware of, we will continue and answer as many questions as we can. And if you have to run by the end of the session is recorded and will be sent to you, and you can listen to all the questions afterwards. So we're just going to carry on here, Joachim, with a lot of interest to your products. So what's the size of the sensitive zone?
Oh, it's below 1 by 1 millimeter.
Okay, thank you. Is there a low power mode for iC-TW39 available?
Yes, you can use the reset pin to enter low power mode.
Okay, thank you. By what is the accuracy of the iC-TW39 limited to 0.1? Explain why it makes sense to use 24-bit for this accuracy.
Accuracy and resolution is not the same. The resolution is ways higher than the accuracy. The limit comes from two different things. One is the sensor, along with the field you apply, and the second is also the interpolation accuracy. So this is rated approximately also 0.1 degrees around this, regarding INL. Regarding DNL, it's even lower. So this plays together.
Okay, thank you. Good answer, thank you. Explain why TMR sensors have to deal with hysteresis effects.
Well, any material around it can introduce some kind of hysteresis. Usually, it is very close to zero. But if you try to measure this, that is a very difficult task to do that. I tried to do it, and I've seen that the system, as demonstrated, is approximately at 100 arc seconds. So that is the minimum hysteresis I have seen. That's why I'm mentioning this value.
Okay, thank you. So the next questions. What is a typical industry use case of a TMR compared to an AMR or an Hall?
We are just starting out with TMR, and I think it's angle sensing for volume application, maybe AC servo feedback, where you like to get a speed input. Those are pole wheels with an MR sensor, interpolators generating AB signals. So this is definitely a larger application, also length measurement. TMR is just coming out, so we will see where it fits into.
Okay, thank you. Is iC-TW39 developed according to functional safety standards?
No, it's not. We, from the engineering, from the design, we did not consider any safety. I just mentioned the compatible to the BIS safety profile, but that does not mean that this chip is already certified for a certain C level. It's not, no.
Okay. Thank you. Is TW39 suitable as an angle measurement encoder comparing to an optical angle encoder?
It depends on your target. The error correction is a dynamic error correction, so it benefits from full revolutions. So if you need a static accuracy on power up, this is ways less good as we demonstrated here. So maybe 5 times or 10 times less good. So this cannot compete with an optical scale where you have immediately on power up the high accuracy.
Okay. Good, thank you. The next questions, or actually there's a follow-up question on this. Is the accuracy scalable by using larger magnets or using magnetic codiscs with more than 2 poles? Can you scale it up?
You may have noted that the TMR sensor is not centered in the package. It's moved to the outer side. It may be possible to reach a larger north-south pole magnet in an even larger distance. That was not covered today, as we are not promoting this as an application target. But I think to a certain way it will be possible.
Okay, excellent. A lot of questions coming in, so I'll just carry on here. About the error, there are 4 waves over 1 turn, which suggests some harmonics. Can this be further fixed?
Well, I can tell you the world is always moving, and so do we.
Okay, thank you. Is it possible to use a 5-volt supply?
No, it's not. This device is purely 3.3 volt only.
Okay, thank you. Is the BIS interface single-ended or differential?
We have 3 pins, meaning single-ended.
Okay. What is the smallest magnet diameter that can be supported?
Well, you can start with 5, maybe 4, 5, 6 millimeters. You will see that the harmonic distortion will be higher, meaning that your position error is not as low as we demonstrated it.
Okay, thank you. When will this product be available on the market? And are there still supply chain issues for this product?
Yes, very good question. Thank you for asking. We demonstrated a fairly new product. So today is just a launch for this product. We are preparing samples, but we aim at Q4 this year to start sampling. So far, we are not impacted for this product, not directly impacted by supply chain issues.
Okay, thank you. So next question, have you compensated Earth magnetic field in your test measurements? How far does it distort?
No, we did not. No,
we did not. Okay.
You need to think of the magnet here provides maybe 60 millitesla in this distance we are reading, and I think the Earth field is ways down.
Okay. Thank you. Can the iC-TW39 be used with a linear magnetic target?
Yes, it's more or less a question we had. When you are using the larger magnets and the sensor is far away, it could be possible to a certain amount. But the distortion will be much, much higher than when using a diametrical magnet.
Okay, thank you. With the linearity, will the linearity stay over the full specified field range as well with the static precision without auto-calibration?
Linearity is compensated by a static correction. And if you change the field, and this may cause that also the TMR changes his harmonic contents. Well, the impact is not this high, but if you aim below 0.1 degrees, it can come visible, yeah.
Okay. Thank you. What are the requirements regarding constant speed during push-button calibration?
Well, push-button calibration for the primary signal errors does not require constant speed, but for the INL correction static here, it is quite beneficial to have constant speed to get an accurate settling. So the engine has no reference, so it needs a constant speed to not to calibrate to the drive's ripple. Imagine if you run very low speed, the drive introduces maybe a 1 per revolution speed change, and so the engine would try to compensate this. Okay. But that's not our measurement. That's not what we need to compensate.
Okay, got it. Thank you. Does the dynamic correction work under condition where it's less than 360-degree rotation?
No, it does not.
Okay. Can the TMR element be damaged with high magnetic fields? What's the max?
Oh, we allow up to 200 millitesla at least, but I'm not confident if it can never be damaged. I don't know what the field strength is. Let me ask this later on.
Okay, thank you.
Let me answer this later.
And now, exactly. And now to the last question. Do you have magnetic rings which will fit the iC-TW39?
No, we don't.
Okay. So this concludes the Q&A session. Really much thank you from us here for the good questions. And if you have any further questions, you can always contact Joachim or Patrick by email, and we will be able to support you and answer to your questions. So that concludes today's webinar. We will look forward to see you on our next webinar, which is coming up on the 5th of April. There we're going to introduce BISline. And as a final word, I just want to talk to you about our social media activities. Please follow us on Instagram, look at our LinkedIn page, and follow our videos on YouTube. These are being regularly updated, and we have some interesting content for you, so we look forward to communicate with you as well over these social media channels. So without further ado, thank you very much for attending, and thank you Joachim, and thank you Patrick for an excellent presentation. See you soon. Thank you. Bye-bye.
Bye-bye.
iC-Haus. Integrated circuits.